In this module, we continue to discuss basic probability and statistics in the context of manufacturing measurement applications. The key concept is that data from repeated measurements usually vary. Distributions of that variation can be modeled and used to estimate the probability of measurements and our confidence that measurements will occur over a specific range. For our discussion of manufacturing statistics and probability concepts, let's consider another example. Imagine a scenario where a medical device company seeks to manufacture a robotic crutch for lower extremity injury rehabilitation. The prototype device was initially researched by engineering students as an actively controlled prosthetic limb, as you can see from this test video. This leg-like device contains a novel EMG-controlled knee joint with a compact ball screw-driven motor capable of power-requisite tasks such as walking up slopes and stairs. Preliminary clinical tests of the product were successful. However, potential customer surveys indicate the device is simply too loud for practical use. If a manufacturing engineer can reduce ball screw bearing noise during the assembly process, they can plan to take the product into production. An obvious place to investigate noise is in the ball bearings. During a key step in the RoboCrutch assembly process, many small bearings are tightly packed around the ball screw within a ball nut assembly, shown at the top right. Unusually high variation in ball bearing geometry could be the source of noise. Consider inspecting a large vendor-supplied box containing a population of thousands of similar-sized small round bearings. In considering bearing noise, we might seek to better understand the size of the bearings and, more importantly, variation in size. But it's not practical to measure all of the bearings, so we might measure 24 from the thousands in the box. This sample of diameter measurement forms a data set which we use to infer information about the entire population of bearings in the box, such as the average diameter and its variation. In statistics, the population is of course all possible values of a measured variable. Sometimes a population is countable, knowable, or even known, but often the actual population is not practically known or knowable. Imagine fish in a lake. The only way to measure the population is to drain the lake, which might not be a good idea for other reasons. In the case of a box of bearings, the manufacturer might not even know the exact number of bearings in the box if they pack it by weight. In statistics, sampling is the process of obtaining data through repeated measurements of a variable, preferably under fixed operating conditions. Drawing a dozen bearings from the box is, of course, sampling. But imagine if smaller bearings settle in a box like this. We have to be careful to ensure the sampling process selects representative samples from the population without bias. In statistics, the sample is simply the subset of values taken from a population, and the measurand is the fancy statistical language name for the variable being measured. In this case, the ball diameter is the measurand. We make measurements that we seek to infer things about the measured variable. The core question is how close are the measurements taken from the small data set at actually estimating the size and variation of all bearings. If selected a different set of 24 bearings, would we expect the values to be the same? What is the average or mean value based on the finite sample? How well does the mean represent the entire population? More importantly, do variations found ensure we meet tolerances for the population as a whole? How good are these results? The questions have their answers in probability and statistics. What are our goals in this type of analysis? Of course, we want to reduce noise, but when it comes to analysis of our sample bearings, we more generally want to be able to quantify 1. A single representative value that best characterizes the average of the measured data, the average diameter of the 24 sampled bearings. 2, we want a representative value that provides a measure of the variation in the measured data set, perhaps the standard deviation, or even the range of diameters. And lastly, we want to know how well the average of the data set represents the true average of the entire population of the measured variable. The value of 1 can vary with repeated data sets, so the difference between it and the true average value of the population is a type of random error. 3 requires establishing an interval within which the true average value of the population is expected to lie. The interval quantifies the probable range of this random error, and it's called random uncertainty. If we want to reach those goals, we need to look more closely at an individual measurement. It's helpful in statistical measurement applications to introduce the notion of a true value, the exact value of a variable. While it is possible that the measured value is the true value, practical limitations often introduce errors, which are the difference between measured and true values. Error sources are diverse. Just to mention a few, errors can be rooted in instrument accuracy, calibration error, human error, data acquisition issues, process variation, or changes over time or temperature, or just natural variation. Even the most accurate measurement instruments with the smallest of resolutions have some real-world limits to their accuracy. And physically, a part like a bearing does in fact have some true size. Simple counting operations like output, yield, or backlog, they might not have error for reliable systems. But measurements of physical or process variables, size, pressure, temperature, force, flow rates, speeds, and key operating variables like time and cost are likely to have errors. Often, an estimate for the value of error is based on a reference value, such as the reference standard during an instrument's calibration, or the range or maximum value. This percent accuracy, also known as relative accuracy or just relative error, is helpful for evaluating a measurement. Notice the absolute value of error is often used as the magnitude of errors is the primary concern. Errors cause a measured value to differ from its true value. We see this particularly when we take repeated measurements of a variable and don't get the same results. Repetitions can be handled differently depending on what we're trying to learn. In our scenario, we independently sample 24 bearings from a box and repeat the measurement of each diameter. Our aim is to understand variation in the entire box. We could also imagine measuring a single bearing repeatedly, say at different orientations around its perimeter to understand its roundedness. Or we could measure the same bearing at different times of day or different temperatures. We could even use different people or instruments to repeat a measurement. No matter the repetition method, if we observe different values of measurements, we classify these differences as errors. We conventionally classify, quote, errors into two main categories: systematic errors and random errors. If we plot measured values by measurement reading number, we can see the systematic errors generally result in an offset from the true or known value, while random errors scatter around the apparent measured average value. In our ball bearing measurements, an offset could be caused by a micrometer calibration error, or even just oil or gunk on the micrometer head. Natural variation in a measurement without a known or controllable cause is generally considered random error. If there is a systematic cause of variation, it generally presents as a systematic offset that can be corrected. Because of this, we initially assume systematic errors are negligible. The average random error is 0, so we assume the best estimate of the true value is the mean value. Dart throwing is a useful illustration of error and accuracy concepts. The best case scenario in terms of accuracy is when all of the darts hit the bullseye. If, however, darts consistently hit the same spot just left of the target, the thrower has high repeatability, low random error, but a systematic error is obvious. A good thrower might be able to correct aim to fix this offset. When dart throws vary around the target, random error is higher and accuracy is low. This illustration is even more helpful when we consider a scenario on the right without a known target. Imagine the target is turned over on the back of the wall. In this case, even the consistent throws, there is no absolute reference for performance. The old saying, "you don't know what you don't know," applies. But we can use statistical methods to estimate and compare errors. As an aside, there's a very cool dart throwing video put on by Mark Rober that you might want to check out on the bottom right. As mentioned, the big challenge with these error concepts is that both the true value of a variable and the actual measurement errors are rarely known exactly. But based on available information, an operator may feel confident that the error is within certain bounds, a plus or minus range of the reading. This range estimate is the uncertainty. Uncertainty is a property of a test result. Uncertainty values are assigned to an instrument or measurement. Formally, our goal is to estimate the true value of a variable x prime using the average observed value, x bar, and apply an uncertainty estimate range u, and then calculate that within some probability p. A sampling of the variable under fixed or controlled conditions renders a sample, which is a finite data set of points. If the number of sample points is very small, the estimation of the true value x prime could be influenced significantly by any one data point. With a larger data sample, the relative influence of any one point becomes smaller. As the number of points increase towards the population size, all variables of the measurand are included in the sample data set. Generally speaking, the more samples we take, the smaller our uncertainty becomes. But most real-world statistics involve finite samples. We'll continue the discussion of measurement concepts in the next module, looking more closely at distributions, probability, and some additional measurement applications.